So some folks may have come in a little bit late. We're kind of, we had to move the sequence of speakers around a little bit. So we are moving now to what is talk number 3 on the agenda. And so we have Evgeny Frolov and his talk, Cross-Domain Latent Factor Sharing via Implicit Matrix Factorization.
Hello, everyone. Thanks for the introduction, Robin. So yeah, I'm here. We'll be presenting the work by my PhD student, Abdulaziz. He unfortunately was not able to get visa, so I'll be presenting the work instead of him. And this is a joint work in cooperation with all these wonderful people here. My name is Evgeny Frolov, yeah. And so let's get started. I'm also going to talk about the cross-domain recommendations, but in a slightly different setup. So I will probably not go into much details for the general setting of the cross-domain recommendations because it was done by the previous speakers. But generally, yeah, what we want to avoid is the problems related to the sparsity of data, which sort of impedes the ability of the recommender system to provide good, like high-quality recommendations. And we also, another aspect for us was to make the algorithm scalable to large data, even though we do not do the study in large-scale setting in this work, but we use the algorithms, which I will explain later, that are highly scalable and were battle-tested in real applications, and well, I can even say right now that it is based on the matrix factorization, which we all heard today that they are still in the focus. There are a lot of interest in applying matrix factorization, in improving matrix factorization algorithms. So this is an attempt to sort of adapt the standard, like well-known framework for the low-rank approximation based on matrix factorization to this specific cross-domain setup. And yeah, and another aspect that we considered, which was not considered in the previous talk, is privacy. So what we want to avoid is sharing any information about user history from any of the domains. So what we want is to find a way to somehow exchange this knowledge between the domains, but avoid explicitly sharing what users has actually interacted with or consumed within each of the domains. And so this leads to a very interesting formulation. So in general, once again, let me just summarize. So we want to develop a very effective, simple, easy to use, battle-tested method that will be able to address the sparsity issues through the cross-domain recommendations, and we want to gain some level of privacy, even though it's not a complete privacy in the sense of, let's say, differential privacy, but there will be some privacy, not guarantees, but some privacy features of the algorithm. So the key ingredient here is to augment the standard matrix factorization. In our case, it was ALS model, well, implicit ALS more specifically, to augment it with the method that will provide sharing of user factors across domains. And it turns out that it can be easily achieved through the ADMM method. And there is a specific formulation for the ADMM sharing in that case. So yeah, this is the general formulation, general setup for the ADMM sharing. So what you see is we want to minimize across in the general setup across n domains the sum of the functions fi, which are just standard loss function for the matrix factorization, and then we have an additional regularization term g of z, where g is some function and z is the special variable that allows us actually to share the information between domains. So you can see that we have an additional constraint that the X factor, which is a user factor matrix in each domain, should be, well, ideally identical to Z, but in the setting of this optimization problem, it will be, we will pull it closer towards Z. So it will not be identically Z, but it will be pulled closer to it. So yeah, this is the general optimization setup, and yeah, and this is how you can actually achieve this goal through the ADMM sharing. So once again, Fi is just standard matrix factorization, like Frobenius norm of the differences between the original matrix of ratings and the low rank approximation. And then we have the additional sort of regularization term with this additional coefficient rho, which actually defines the strengths of sharing, like how much do we want our model to depend on this sharing aspect, right? How much do we want that our model, our in-domain models depend on the information from another domain, like from the outside. And so this is, you see that along with this new variable Z, we have this additional like slack variable U, which actually allows for some differences across domains. Like users are still not identical in different domains. They may still have some like variation in their preference, in their behavior. So pulling all factors xi, that's all user factors, to just a single representation across all domains may be not that useful. So this slack variable U allows to somehow account for that possible deviation. And then, so what we do is the first step is just like standard matrix factorization. You just optimize it using standard tools with this additional regularization. And then we have two additional steps in addition to the standard matrix factorization step, is that we find this Z variable, which is a sharing factor, right? That's something that accumulates the knowledge across all domains about the user behavior, about their patterns, like consumption patterns. And another, like the third step is, well, this update for the slack variables within each domain, like that allows us this, that enables this deviation from the common, like global pattern. And yeah, so there are slightly more details, like we have this proximal operator for updating Z. In our case, it was just identity. So it all follows from the ADMM sharing approach. So if you're really interested in that, you can read in the paper, or you can ask me afterwards. I will not go into talk about it in detail. So, but you see that generally it's very straightforward. So it's just standard matrix factorization with two additional steps, and they are very easy to implement. And so the sharing happens, as I already explained, through this Z variable, which is computed through the accumulation of this like global, like summarized representation of user factors and summarized representations of these slack variables, right? So it's like almost like an average representation. So effectively what it does is that if you have like two domains, you have two representations of the users, and so the slack variable will be somewhere in the middle, and then the 2 points representing the factor matrices of the two domains, right? They will be going closer to each other, right? They will not collapse into a single point, but they will be pulled closer together. So this is like the how you can like geometrically imagine the process of this optimization. And yeah, so we used standard experimental setup. We just we didn't invent a new setup, so it's not an ideal. So we use this negative sampling for computing the matrix. So matrix will be a little bit biased. We use standard datasets which we found in the preceding literature, and we used a number of both cross-domain and standard classical approaches to evaluate against and compare against. So you can see that there are standard, like both classical methods, like matrix factorization methods, and more recent neural network-based method. And the same holds for the cross-domain setting. Well, for the cross-domain algorithms, they also present. Well, they are mostly neural network-based. Okay, so and we have these two setups: the warm start and a cold start. So let me start from the warm start setup. Actually, it's a little bit of abuse of definitions. So in the normal, not cross-domain setting, it would be just standard collaborative filtering. So what we do is we have these two domains presented in the picture on the top left corner. So we have two domains. We just discard all the users that are not shared across domains. So we only leave the users that are shared by both domains, and we train the model that I presented on the previous slide just normally as it was formulated. And again, it is warm start because, well, we learn not straightforwardly user representation, but we sort of update it through the knowledge, with the knowledge coming from another domain. So it's not the same user as if it would be when we train just a single domain model, right? So again, it's a little bit of abuse of the definition, but okay, let's go with warm start. And so in that case, the results are presented in the bottom part. So we have two pairs of data sets. So that's one, for example, source data set, and another one is the target data set. Actually, there is no difference between source and target. So our approach is totally symmetric. They at the same time, they both source and target, so you can use it interchangeably. And so on some data sets, like for example on sport and clothes, that's the left, like the red-blue color bars, that's two metrics. Blue is hit rate and red is NDCG. We see that our approach, which is top right bar, outperforms all other methods in both data sets. All methods, including the single domain, cross domain, neural network based, and even the ALS method that was trained in just single domain setting. So it's like this, it's as if this raw factor was set to 0. You remember the raw factor that was corresponding to raw coefficient that was that correspond to the sharing term, to the sharing regularization. On the right side, we see a little bit different picture. So we didn't improve much over the baselines, but this pair of data sets is a little bit strange, a little suspicious, I would say, even though we do not understand exactly what's happening there, but we provide this ALS separate as a third pair of bars. So the ALS separate, as I said, it's just single model which is identical to ours, or a single domain model which is identical to ours. So it's the ALS without sharing, and it performs, in some cases, it performs better than all other methods, including cross-domain. So there is something tricky in this going on. So something is about these data sets that makes it harder to share knowledge across domains. Maybe we can use our model as an indicator for like complexities in the data, but it's not clear. And more interesting setting is the cold start scenario, where we do not discard the users and we test a unseen set of users in each domain. So those users were not shared during the training. We use the knowledge from another domain to generate recommendations to those users in the target domain. Right? So that's why this is a classical definition of cold start. Right? We want to predict new interactions for the user that does not have any interactions in the current data set. In that case, we again see that for the left part of the left pair of data sets, our model was able to outperform all other baselines. On the right part, we see again some asymmetry. So on one data set, in one direction, we were able to improve the results, but in another direction, we were not able to improve the results. Maybe it's related to sparsity. It's hard to tell right now. Again, we continue investigating this. So these data sets, at least, they're very different in sparsity. But maybe it's just hard to guess what people will watch, considering what they play with, right? Or what games do they play? So yeah, but a lot of speculation can be done there. So yeah, that's. I'll probably skip the slide. I just wanted to highlight the effect of this sharing parameter, the sharing coefficient rho. So you can see that if we increase the value of rho, it's different colors presented on the graphs. The general quality increases, but if we set rho too high, you see that drop. And the drop just, it's very logical. So we regularize our our sharing mechanism to sort of penalize user factors to make it closer, so they become very close to zero actually, because it's still hard to make them identical across all domains. So they become close to zero, and then in order to recommend something, you need the item factors to be large, the norms of the item factors to be large. But we have this special regularization based on the popularity of items, and then it's, the only way for the model to sort of generate recommendations is to promote those items that have low popularity. And so that's what we see, that this drop, it corresponds to the new regime where the model starts recommending something irrelevant, like non-popular items with smaller norms. Okay, yeah. Of course, the quality depends on the aggregation frequency, like how often do you do this sharing step? You are not obliged to do this at every iteration of your matrix factorization update. So, of course, the more frequent the updates are, the higher the quality, but still, like, you can do like every second or every third or every fourth step, and the quality drop is, well, it's noticeable, but not that significant. So, yeah, with this I want to conclude this work. So again, we used the ADMM approach to enable sharing across domains. The underlying model for learning factors was ALS, but actually you can use some other model. So we haven't explored it yet, but it is possible. It doesn't depend on the choice of the base model. So this ADMM sharing is more or less universal in that sense. So it provides a competing quality, even though there are some peculiarities that I described, and it requires additional investigation. But still, it offers a very simple and very easy to reproduce approach. And yeah, we hope that it will find its use in some real applications. Yes. Thank you for your attention. I'm ready to ask you questions, and this is just future work if you're interested in.
All right, let's thank the speaker. So we are short on time, but there is one question that kind of came up in several different forms in Slido here. And the question is, it's about the constraint, the sort of the x minus z constraint. Mm-hmm. Would it be possible to replace that with a sort of squared loss that you add to the objective function as opposed to treating it as a constraint? And what would be the trade-off in doing that? Yeah, so yeah, thanks for the question. Yeah, actually, you can do this through the collective matrix factorization hybrid scheme. So yeah, it is possible, but it then becomes hard to make this sharing like easy to use across domains. So in this ADMM setting, what we share across models is this additional z, which is like sort of calculated locally, and then it's updated with local slack variable, and only this sum of the factors is shared. And this provides additional privacy. In collective matrix factorization framework, it will probably be different. We will probably need to share the exact user factors, so it will be less private in that sense. So it will be easier to restore user factors if you have like if you assemble like man in the middle attack, for example. You can still try to restore user factors, but in the ADMM sharing approach, we obscure the factors of the users. All right, I think we'll have to leave it there. Let's thank Evgeny again.